My name is Ayoub Alwan. I'm CTO Academy at Servio Group, and today we will talk about how to craft resilient integration solution. And really, why I choose to talk about this subject is because it becomes my daily work, and I always wanted to share my experience and my knowledge with others in the community. And it will be my first time that I will give this talk, so I'm so sorry if there is something missing or something like that. And thank you. So we will start now. So, so before starting our talk about integration solutions, we should establish some context. So the first question to ask is, what brought us to here? Why we are talking about this subject? The answer is not simple, but because it depends on problems that perhaps modern developers have not faced. So if you are working in a large company, you may constantly wonder how you arrived at the current state and what may have been overlooked. If you're an architect or someone with a role that's complex to define, by examining multiple projects within your company, you will notice that applications have cohesion among them. Yet, they are designed as if this isn't the case. This is often due to lack of long-term vision. If these applications need to share information with each other, we are faced with a difficult technical and management process. So, because each app belongs to a different department and may be developed using different programming languages and tools, here I'm trying to highlight the importance of service-oriented architecture. So perhaps members of the hierarchy are hesitating to collaborate and discuss their apps, but they need to, because they should offer a good service to the user at the minimum cost. Otherwise, another company will do. So when we are talking about sharing information between apps, we are talking about services. We are not referring to someone who will write an information on a sheet of paper and send it to a member of another team, who will then manually input it into their app. That method, it's not inefficient. It's not efficient. Okay, that's not what we are considering. We are trying to find a modern way to transfer messages that need to be secure, reliable, monitorable, manageable, and finally, loosely coupled. It means that we should integrate our applications into a system so that they can communicate and share messages. But do you think that we started with a perfect solution? Of course not. So let's take a deep dive into history. We will start with P2P integration. After that, we will talk about central EIE broker, and we'll finish with enterprise service bus. So point-to-point integration was the first method employed to achieve integration between apps. Before explaining how it works, here is a figure that illustrates how point-to-point architecture functions. The point-to-point integration approach connects two apps with a direct relationship. Imagine we want to establish a communication between house 2 and house 1 and house 2. Using a P2P connection, we would have a direct line between the two. It means that if the line goes down, we will lose the connection between the two houses. Therefore, we cannot confidently say that we have a reliable system. If we wanted to add a house 3, we would need to add additional lines between houses 1 and 3 and 2 and 3. This means that our houses are tightly coupled. It's also insecure because we have a direct relationship, which becomes a single point of attack for spying on our data. Moreover, it's not monitorable, okay? Because we can't easily keep track of our communication due to the lack of a central monitoring system. And finally, it's not manageable because managing direct lines between a large number of houses is challenging. Now we can draw a parallel between houses and a service-oriented architecture. For instance, as seen in this diagram, service CRM is directly coupled to HR. HR is directly connected to finance. This setup is risky because if we make changes in the finance service, we must initiate a new integration process to adapt to all other services. And that's a laborious task to undertake each time we need to make modifications to the services. So, is this approach still applicable? Clearly not. After P2P, we moved on to something called central EIE, okay? Enterprise Application Integration Broker, which is better approach. Let's explore this in the following slide. So, to be clear, this approach resolved all the point-to-point issues by connecting applications through a centralized system. And that's the key word, centralized. So If we want to benefit from this approach, the leaders of each project or service must give up control to a centralized infrastructure, okay, where each service is integrated. Thus, our system will be secure, reliable, loosely coupled, monitorable, and manageable. But we will lose some control over our services. Perhaps this seems a bit complicated. Let's simplify it with a real-world example. Imagine our city has a single central post office. Instead of each person delivering their mail directly to the recipient, that's the point-to-point architecture. Now we need only to have the address of each recipient and send the mail to the central post office, which has complete control over the delivery process. This centralization ensures a secure process because the post office has invested in reducing the risk of theft or loss to a minimum. Additionally, the post office can easily monitor and manage mail through a system that keeps track of every parcel sent and received. This method is an improvement over the previous systems, which was established to expedite mail delivery. If necessary, the post office will establish new processes to ensure delivery without involving the sender and the receiver in these issues. Just like the post office, the central EEI broker, enterprise application integration broker, features a central hub responsible for the routing, security, monitoring, and transformation of data to ensure it is in formats that can be understood by the receiving service. Like we see, this architecture is great. It solves all of the P2P problems, but it created a new one. We now have a single point of failure. If the central hub go down, all the communications will fail. And it's really difficult to communicate with a service that we can't integrate into our centralized AI broker because it's an external one that doesn't belong to our company. So there is a lot of problems with this architecture. So, and here comes the enterprise service bus. That what so which ASB though is giving back the control of the apps to their owners and not integrating all the apps in a central hub, but giving access only to business functionality. Now our system will be scalable easily. The integration here is more easy. We will have to deal only with business services that will be connected via virtual channels. No need for direct connection between services. This architecture may seem a little bit complex. So to simplify that, I will stick on our post office example. So instead for having one centralized post office, imagine that we have multiple small post offices that are connected via dynamic routers that can change easily if a route doesn't function. For example, if a post office has a problem, the mail is simply rerouted through other offices. That means there is no single point through which all mail must pass. Instead of that, each post office can handle mail, sort them, forward them to their destination, to pass them to another post office that is closer to their destination. So there is no single point of failure. The system is resilient. It can scale easily all of that because it's decentralized. So to implement these types of architecture, really to have resilient and integration solution, we should use some patterns. Okay, so here in this talk, I will try to highlight some known because I can't have time to highlight all the patterns that we have in enterprise integration solution. So I will try to highlight some ones. So let me take a little bit of water. So I will start with the aggregator pattern. Okay, so in the aggregator pattern, the aggregator pattern is a crucial component in enterprise integration. The aggregator is a stateful filter that plays a vital role in collecting and storing individual messages until it receives a complete set of related messages. It's primary. I received it's working good. Okay, great. So its primary purpose is to enable the processing of multiple related messages as a single cohesive unit. This pattern is essential when dealing with complex message flows where information arrives in fragments or from multiple sources. The aggregator pattern consists of three key components: correlation, which determines which messages belong together, the completeness condition, which defines when we are ready to process the collected messages, and the aggregation algorithm, which specifies how to combine the received messages into a single result. Understanding these components is crucial for implementing an effective aggregator in your integration solutions. So let's dive into how the aggregator pattern actually works. As we can see in this diagram, the process begins with incoming messages. Each message goes through a correlation check to determine if it belongs to an existing aggregate or if it should start a new one. If there is a match, the message is stored in the corresponding aggregate. If not, a new aggregate is created. After each addition, the aggregator evaluates the completeness condition. If the condition is met, it means we have all the required messages, and the aggregator can then publish the combined message. So, if the condition isn't met, the messages are properly grouped and processed together. So, if it's not met, the aggregator continues to wait for more messages. The cycle repeats for each incoming messages, ensuring that related messages are properly grouped and processed together. The beauty of this pattern lies in its ability to handle asynchronous and out of order message arrivals, making it invaluable in distributed systems where message timing can be unpredictable. So, when implementing the aggregator pattern, choosing the right aggregation strategy, because there is not one, is crucial. Let's explore four common strategies. First, we have the wait for all approach. This strategy is ideal when you need complete information before processing. For example, if in order fulfillment system, you may wait to the confirmation from all departments before proceeding. The second strategy is timeout. Here you set a specific time limit for collecting messages. This is useful in scenarios where you need to balance completeness with timeliness, such as in binding system. The third strategy is first best. This approach is all for situations where you need quick results and subsequent response are less critical. Okay. Uh, Lastly, we have the external event strategy. In this case, the aggregation concludes based on a specific business event, like the end of a trading day in financial systems. Each of these strategies has its place, and the choice depends on your specific business requirements and system constraints. Okay? So, implementing the aggregator pattern requires careful consideration of several key factors. Okay, first and foremost is state management. Since the aggregator needs to store partial aggregates until they are complete, you need an efficient way to manage this state, possibly using in-memory data structures or even persistent storage for reliability. Next, you need a robust correlation mechanism. This could be based on message, properties, content, or even custom logic to accurately identify related messages. Error handling is another critical aspect. You must decide how to deal with missing or late messages. Do you time out, send alerts, or perhaps have a recovery mechanism? Scalability is also crucial, especially in high volume systems. Your implementation should be able to handle multiple concurrent aggregations efficiently. Lastly, don't forget about monitoring. Implement ways to track the status of ongoing aggregations and measure performance. This will help you identify bottlenecks and optimize your system. By carefully addressing these considerations, you can create a robust and efficient aggregator that significantly enhance your integration capabilities. So now we'll talk about the second integration pattern, message channel pattern. But don't forget about the first one because we will do a small demo of the first one, okay? So the message channel pattern is a fundamental concept in messaging systems. A message channel can be thought of as a virtual pipe that connects application within a messaging infrastructure. Its primary purpose is to enable reliable, asynchronous communication between different parts of a distributed system. Think of it as the postal service for your applications. It ensures that messages are delivered to the right recipient in the right order, and with the assurance that they will not be lost along the way. There are two main types of message channels: point-to-point channels, which ensure that only one receiver consume any given message, and publish subscribe channels, which allow multiple subscribers to receive the same message. Understanding these channels types is crucial for designing effective messaging architectures that meet your specific communication needs. Okay, so let's break down the anatomy of a message channel to understand how it functions. As we can see in this diagram, the process begins with a sender application. This could be any part of your system that needs to communicate information. The sender sends a message to the messaging channel. The channel then stores this message in a queue or a topic, depending on whether it's point-to-point or publish subscribe channel. The message waits here until a receiver is ready to process it. When ready, the receivers relieve the message from the channel. Is through this process, a channel manager oversees the operation, handling tasks like creating channels, managing their life cycle, and ensuring message delivery. This structure allows for loose coupling between senders and receivers, as they don't need to be aware of each other's existence or be available at the same time. It's this decoupling that makes message channels so powerful for building flexible, scalable systems. So now that we understand what message channels are and how they work, let's explore why you may want to use them in your systems. One of the primary benefits is the decoupling of components. By communicating through channels, your applications don't need to know about each other directly, making your system more modular and easier to maintain. Asynchronous communication is another key advantage. Senders can fire and forget, continuing their work without waiting for a response, which can significantly improve system responsiveness. Message channels also enhance scalability and fault tolerance. You can easily add new receivers to handle increased load, and if a receiver fails, message can be delivered when it recovers. Many messaging systems also offer persistence and guaranteed delivery, ensuring that messages aren't lost even in the face of system failures. As for use cases, message channels excel in distributed system integration, forming the backbone of event-driven architectures. They are great for load balancing and work distribution, allowing you to spread tasks across multiple workers. Lastly, they can act as a buffer, smoothing out spikes in processing and optimizing overall system performance. So, implementing message channels in your system requires careful consideration of several factors. First, think about your channel naming and organization strategy. A clear hierarchical naming convention can make your system much easier to understand and manage as it grows. Okay? Security is another crucial aspect. Implement proper access controls to ensure that only authorized application can send and receive on specific channels. Message routing and filtering are also important. Consider how you will direct messages to the right channels and how receivers can filter incoming messages to process only what's relevant to them. Don't forget about monitoring and management. Implement tools to track channel performance, message volumes, and potential bottlenecks. Lastly, pay attention to performance tuning. This may involve adjusting channels buffer size, implementing message compression, or fine-tuning your message middleware configuration. By addressing this consideration, you can create a robust messaging infrastructure that serves as a reliable communication backbone for your entire system. So now we will talk about publish subscribe channel pattern. Publish subscribe channel pattern, a powerful tool for image broadcasting in distributed systems. At its core, a publish subscriber channel, often called PubSub channel, is a special type of messaging channel that delivers a copy of each message to multiple receivers. Its primary purpose is to efficiently distribute events or information to multiple interested parties simultaneously. Okay, so the key concept here is the decoupling of publishers from subscribers. Publishers send messages to a topic without knowing who will receive them, while subscribers express interest in one or more topics and receive messages from those topics without knowledge of who published them. This decoupling makes PubSub channels incredibly flexible and scalable, allowing for dynamic addition or removal of subscribers without affecting the publishers or other subscribers. So let's dive into how publish subscribe channel actually work. As we can see in this diagram, the process begins with publisher. This could be any component in your system that has information to share. The publisher sends an event or message to a topic. Think of a topic as a broadcasting station. Once the message reaches the topic, the magic happens. The PubSub channel creates a copy of the message for each current subscriber and delivers these copies simultaneously. In our diagram, we see three subscribers each receiving a copy of the message. An important feature to note is the ability to dynamically add new subscribers, as shown by the dotted line. A new subscriber can join at any time and will start receiving messages from that point forward. This dynamic nature is what makes PubSub channels so flexible and powerful for building event-driven architectures. So, I will drink some water, please. So, the publish subscribe channel pattern offers several significant advantages that make it easier a go-to solution for many scenarios. One of the primary benefits is the loose decoupling it creates between publishers and subscribers. This means you can modify either side without affecting the other, leading to more maintainable and flexible systems. Scalability is another key advantage. You can easily add new subscribers to handle increased load or new requirements without any changes to the publisher. Flexibility is also a strong point, as subscribers can often filter messages based on content or metadata, ensuring they only process relevant information. Additionally, PubSub channels excel at real-time event propagation, making them ideal for systems that need to react quickly to changing conditions. As for use cases, PubSub channels are perfect for news feed systems where multiple users need to receive updates simultaneously. They are extensively used in stock market data distribution, allowing multiple traders to receive, for example, real-time price updates. In the Internet of Things domain, PubSub channels efficiently broadcast sensor data to multiple monitoring and analysis systems. Lastly, they are a key component in many real-time collaboration tools, enabling instant updates across multiple clients. So, implementing the publish subscribe channels in your system requires careful consideration of several key factors. Okay, first, think about your message delivery guarantees. Do you need at least once delivery? Or is it okay if some messages are occasionally missed? This decision will impact your choice of messaging middleware and how you handle edge cases. Subscribes management is another crucial aspect. Consider how subscribers will register and unregister from topics, and how you will handle inactive or slow subscribers. Topic naming and hierarchy is important for organizing your event space. A well-designed topic structure can make it easier to manage and scale your system as it grows. Message filtering is another consideration. Decide whether filtering should happen at the channel level or the subscribe level and how complex your filtering needs are. Lastly, pay close attention to performance and scalability as the number of publishers, subscribers, and messages grows. You might have need to implement strategies like messaging batching, load balancing, or even custom optimization in your messaging infrastructure. By addressing this consideration, you can create a robust PubSub system that efficiently handles your event distribution needs. So now we'll talk about process manager pattern. So the process manager pattern, a powerful tool for orchestrating complex workflows in distributed systems. At its core, a process manager is a central component that maintains the state of a sequence of steps and determines the next processing step based on intermediate results. Its primary purpose is to manage and coordinate complex multi-step business processes that may involve multiple services or applications. The key concept here is centralized control of distributed processes. Unlike simpler patterns that might use predefined sequence of steps, the process manager can make decisions on the fly, adapting the process flow based on the results of each step. This makes it incredibly flexible and capable of handling complex business logic that may be difficult to implement with other patterns. Let's dive into how the process manager actually works. As we can see in the diagram, the process begins with a trigger message. This could be a customer order, a system event, or any other thing that kicks off a business process. The trigger message is received by the process manager, which then makes a decision about what step to execute first. The decision is based on predefined rules and the content of the trigger message. The process manager then initiates the chosen step, which could be a call to a microservice, a database operation, or any other tool, any other action. Once that step completes, it returns a result to the process manager. The process manager then uses this result along with its internal state to decide on the next step. The cycle continues with the process manager orchestrating each step until the entire process is complete. At that point, the process manager produces the final output. Decentralized decision making allows for complex conditional workflows that can adapt based on the results of each step. So, the process manager pattern offers several significant advantages that make it invaluable for complex business processes. One of the primary benefits is the centralized control. It provides over complex workflows. Centralization makes it easier to understand, monitor, and modify business processes. Another key advantage is its ability to handle long-running, stateful processes. Unlike simpler patterns, a process manager can maintain state over extended periods, making it perfect for processes that may take hours, days, or even weeks to complete. Flexibility is another strong point. The process manager can adapt the process's flow based on intermediate results, allowing for dynamic, condition-based workflows. Additionally, it provides improved visibility and manageability of business processes, as all the logic is centralized in one component. As for use cases, process managers excel in scenarios like order fulfillment systems, where multiple steps like inventory check, payment processing, and shipping need to be coordinated. They are also ideal for insurance claim processing, where the steps may vary based on the type of claim and its complexity. Booking systems often uses process manager to coordinate flights, hotels, and car rentals. Lastly, they are perfect for multi-stage approval workflow, where different approvals may be needed based on various conditions. So, implementing a process manager in your system requires careful consideration of several key factors. First and foremost is state management. You need to decide how to persist the state of each process instance, ensuring that it can be recovered in case of system failures. This often involves using a database to store process states. Error handling and recovery are crucial. You need to design how your process manager will handle failures at various stages and how it can resume processes from the point of failure. Scalability and performance are important considerations, especially for high volume systems. You may need to implement strategies like sharding or load balancing to distribute the load across multiple process manager instances. Monitoring and logging are essential for maintaining and troubleshooting complex workflows. Implementing comprehensive logging of each step and decision made by the process manager. Lastly, consider how you will define and version your processes. Many implementation use a domain-specific language or visual tools to define processes, and you will need a strategy for versioning these definitions as your business processes evolve over time. By addressing these considerations, you can create a robust process manager that effectively orchestrates your complex business workflows. So, now we have studied four integration patterns. I told you that you don't forget about the aggregator one. So here I will try to give you an example of enterprise integration solution that exists in the market. There is, for example, Apache Camel, there is MuleSoft, and there's a lot of other solutions that you can use. There's a lot of solutions, so you don't need to code all of these integration patterns. Maybe for if you have more complex use cases, but there is tools that do that for us. For example, here we will try to understand how MuleSoft, the solution for integration solutions, can are implementing the aggregator. We will see how they implemented the aggregator. So here we can see diagram. Now we will try to dive into MuleSoft time-based aggregator. Here we will only see the aggregator with the time-based that will take, for example, that will aggregate results every 5 minutes. Okay, so and we'll see how it's implemented. Let's start with our Mule flow. This is the first class. Imagine orders following into our systems. Order for 5 shirts, order for 3 pens, and so on. As these orders arrive, the Mule flow calls the execute method on our time-based aggregation operation executor. It's a class there. This executor then calls the aggregate method on the abstract aggregator executor. Think of this as the brain of our operation, coordinating all the moving parts. First, the abstract aggregate executor reaches out to the object store, our persistent storage. Here we are talking about the state management, our persistent storage. It's like a digital filing cabinet retrieving any previous aggregation state. If we start already the aggregation, he will see if there is one. He will retrieve it. For example, it may recall last time we had processed 50 orders. He will take the orders that he needs. Next, we get our simple aggregated content. This is our aggregation basket where we will collect all the orders for the current 5 minutes. We'll collect them there. Now, here is where the time-based magic happens. We will call a register async aggregation if needed. It's a method setting up a task to run every 5 minutes. It's like setting a kitchen timer for our aggregation. It will run for 5 minutes. As each order comes in, we call add storage on our simple aggregated content. It's as if we are putting each order slip into our aggregation basket. Okay? After processing each order, we update our shared information in the object store. It's like updating our tally sheet. Okay? So this process repeats for every order that arrives within the 5 minutes that we decided. Now let's fast forward 5 minutes. Our timer goes off. It's finished 5 minutes. So here on async aggregation execution is called. This is where we process all the orders we've collected. First, we call get aggregated elements on our simple aggregated contents. It's like dumping out our basket, okay, of orders. Next, we check if anyone's waiting for our results. In Mule, we do this by calling get listener in the aggregation manager. You will see all of that in the demo. If there is a listener, we notify it with our aggregated data using notify listener on complete. It's like calling out. In the last 5 minutes, we proceeded 20 orders. Finally, we call receipt group. This clears out our simple aggregated content, ready for the next 5 minutes window. It's like emptying our basket, ready to collect new orders. What makes this approach powerful is its efficiency. We're not storing every single order forever. Instead, we are summarizing our data every 5 minutes, providing regular insights into our sales. So this pattern is incredible. While we've talked about order processing, you could use it for time-based data, monitoring website traffic, for example, count visits every minute, tracking stock prices, aggregate prices. You can use it for a lot of use cases. So here we will try to see a real demo with MuleSoft and how we can implement that very fast with MuleSoft. So here I will share now. So how can I share that? So it should be like that. Okay, great. So I will share my screen now. So here I will share my screen with you so you can see the demo. Okay, great. So here with MuleSoft, I will create a flow of this aggregation. I will create a new one here because I was trying to prepare the demo for this talk. I will name it C# conference. Okay, so it's very simple. Here I will call an aggregator. I need a time-based one. It's here. Here what I will try to do is I will try to log what the aggregator is doing. And how I can call this aggregator, I will define an HTTP listener to call the aggregator. And what we said before, we need an aggregator listener for the ending of what the aggregator is doing. And here I will add a simple transformer to transform our message that we will print to show you in the logger. Here it is. And here I will also add a transformer so we can see our logging. Okay. So now I need to configure my components. It's not working now. Okay. So I will go to the listener. I will choose the listener. It's one that I already set up here with this port. Okay. So I will go to the time. Here I will define the I will define no, it's not here, it's here. That's what we do in demos. I should not let that. Okay, so here I will call the listener that I just created. Here I will call it here, and I will call a pet conference. Okay, this is the pet. Here I will call my aggregator. I will name it time conference. Okay, we should not forget it. Every 10 seconds he should run, every 10 seconds. Here I will transform my message to JSON to print it, so it will be cool. Here I will call it in my logger. Here I will configure my listener. I will tell him, listen, my listener aggregator, listen for this aggregator. I copy paste the name. And here I will use my transformer to transform the payload. And here I will print it. Okay, cool. So now I will try to run my demo. Hope it will work. And what I should do is that I should call my, I name it what? Conference, I think. Conference, yes. So here I have my MuleSoft running, and my flow is running now. I can see it. And here I can see how the aggregator is working. So we will wait for the process. It's cool. Now it's working. So I will clear the console. So I will get nothing, so we can show the results. Here I will call conference, and I will send it some, I will say t-shirt. And after that, I will say pants, for example, 9 t-shirts. So here, when I will look with me here, you will see something. So when I will click, I will get the t-shirt. Okay. Here I will tell him I want 6 pants. They started counting for the 10 seconds. Here I have, now he aggregates that for 9 and 6. Okay. So here maybe I did something. I forget I forget the payload. Okay. Sorry for that. I forget to print the final payload. So sorry for that. I will rerun my process now. So here I will try to show you how it works. I think I'm running out of time. I'll try to do my best to finish. So here you can see with me. I will clear my aggregator. Okay, my console. Is it working? Is it finished? Yes, great. So I will clear this. Here I will call conference slash pants 6. Here I will add 4 t-shirts. Call it now. He aggregated 6, 4, and the final state is 6, 4. So to show you how it works, maybe I should copy paste a simple total. So here we will use this code to show you how he will calculate at the end the total of our orders, for example. Okay. So I will rerun the last time. This is really the last time. Don't stop like that. Okay, great. So here we will see how he will aggregate results, and at the end he will print us the total of what we orders. Okay, so here I will try to call it very, very, very fast. Okay, I have a t-shirt. Let's do it. Let's do it. Great. Yeah, I have 1 minute. So clear it. Now I will call conference on t-shirt. They have 4. I call pants with 5. And here, after the 10 minutes will finish now, he will make the calculation total 9. So we aggregated and do some work to get us, for example, now 9 orders for the total for the 10 seconds that we configured in our time-based aggregator. So thank you so much and see you. Bye bye.